Today, we are 3D printing a transparent microfluidic chip. It's like a circuit board, but for air. Then we give it a mechanical brain, add legs, and make it walk. On this channel, we've built a few soft robotic creatures, like this tiny bipedal walker, a wiggly snake, and 2 salamander-style bots. They are powered by air, and these squishy muscles make them move. Their design is inspired by something I found in an air pump, a rolling diaphragm membrane. Pull a vacuum, it contracts. Push in air, it stiffens. Pneumatic systems aren't new. But here we are working on a much smaller scale. We are entering the world of microfluidics. Micro refers to the size of channels, usually micrometer scale. Though, to be fair, our bots sit right between micro and millifluidics. Okay, small channels. But what is fluidics? It's a mashup of fluid and logic. A fluid can be a liquid, like water, or a gas, like air. And logic? In electronics, logic is about making decisions, flipping signals on or off, based on certain rules. It's how computers add, compare, and process data. In microfluidics, we can do something similar. But instead of controlling the flow of electrons, we are controlling the flow of fluids. For example, an inkjet printer is basically a microfluidic system, firing droplets of ink with incredible precision to form text and images. This is actually part of a whole field of droplet microfluidics, where fluids are controlled one tiny drop at a time. Or take these at-home COVID tests. The liquid sample moves through the strip via capillary action. That's paper microfluidics, using the structure of paper itself to move fluids. One of the big motivations behind microfluidics is replacing slow, error-prone manual pipetting with automation, ideally shrinking an entire lab onto a single chip. But what does this mean for our squishy bots? So far, every one of these robots has relied on a bulky external setup. I call this setup the electrofluidic system because it acts as a kind of bridge between electronics and fluidics. And while that works, one of my long-term quests is to give these little creatures more autonomy and integrate the electrofluidic system directly into their body. So far, our bots have used pretty simple microfluidic systems, just static channels that split and route air. I like to think of microfluidic systems a bit like printed circuit boards or PCBs. You've probably seen them, those green or yellow layers inside phones, laptops, or really anything electronic. They've always reminded me of tiny cities. The copper traces are like roads. Instead of cars, it's electrons that move on these roads. But what actually gives these little cities their function are the buildings. Tiny components called surface-mounted devices. And as the name suggests, are mounted on the surface of the board. These are the brains of the operation. They switch, regulate, and process electricity. Right now, we've only built the roads, the channels. They move air from A to B, but they don't do much along the way. And we add fluidic versions of surface-mounted components. One classic example is an elastomeric valve. 2 channels intersect, and between them sits a flexible, squishy membrane. Apply pressure to one channel and the membrane expands into the other, blocking the flow. It lets one channel control the behavior of another. By playing with that idea, fluid equivalents of electronic components such as diodes or transistors can be built. And if you combine those cleverly, you can create oscillators, circuits that produce rhythmic outputs. And rhythm is exactly what we need. From our earliest walker to the latest squishy salamander, they all rely on rhythmic air pressure to move. But building a fully integrated all-fluid oscillator from scratch is a lot. Is there a simpler way to get an oscillating output? Well, have you ever squeezed a ketchup bottle and it started to sputter? Most people hate that, but some researchers saw potential and turned that sputter into a feature. They built soft valves that transform a constant stream of air into an oscillating output. And when you chain them together, they begin to self-sequence, activating one after the other. It's super elegant, but cutting the tiny slits is tricky, at least without a laser cutter. But then I remembered this, a mechanically driven rotary valve. These are actually used in commercial lab-on-a-chip systems. You could think of it as a mechanical oscillator. It's not logic in the digital sense, but it could give rhythmic output. This seems like a good first thing to explore. Here's the full plan. Print a microfluidic chip with an integrated rotary valve, and then give it some legs. The first design I came up with is pretty simple. One port for positive pressure, one for negative pressure, and one output. To connect them, I added this bridge channel. This bridge can rotate freely to connect either one of the inputs to the output. The input and output channels are located in a flat base, and the bridge in the rotor on top. A central screw acts as an axle, and for the valve to be somewhat airtight, the contact surfaces between base and rotor need to be as flat as possible. But flatness isn't exactly a strength of filament printing, unless you take into account the smooth surface of the build plate you print on. By orienting the valve parts towards the build plate, we should get a quite smooth contact surface. Microfluidic chips are often made from transparent materials, so you can see what's going on inside. I wanted to try something similar, and while I'm definitely not the first to explore transparent 3D printing, I was curious how far I could push it. By switching to 100% infill and tweaking my print settings, I got this. Not crystal clear, but good enough to see the tiny channels. And it also seems a lot more airtight. Alright, back to the rotary valve. With the new settings dialed in, I printed both the base and the rotor on a smooth build plate. The underside came out pretty flat, and you can just make out the tiny bridge channel inside. Same here. You can clearly see the 3 input and output ports. To connect to the channels, I tapped in some blunt needles. I added a spring around the screw to press the rotor and base together so they seal but still spin freely. Finally, I locked everything in place with a nut. And there it is. Now, let's test it. To visualize the air pressure, I cut out a dome from this fidget toy and sandwiched it between 2 printed parts to create a simple pressure indicator. When we push in air, the dome pops out. Pull a vacuum and it snaps back in. Let's try it with this pump. It has two ports. One pulls air, that's the vacuum side. The other pushes air, that's the pressure side. Let's connect everything. The pump, the rotary valve and our pressure indicator. And it worked. We can switch between vacuum and pressure just by rotating the valve. Though you do need to hit just the right angle. So let's see if we can improve on that. This second design keeps the same basic idea. Two inputs, one for positive pressure, one for vacuum. But now, instead of single holes, the inputs end in these arc-shaped segments. And the output, it's a full circle surrounding them. On top, there's again a bridge channel. But now, as it rotates, it smoothly connects one input segment to the output and then the other. This makes alignment much easier and gives us more flexibility in how we drive the rotation. Once again, I printed both parts. You can clearly see the tiny bridging channel inside the rotor. Love that detail. And here are the grooves for the two input arcs and the circular output. After hammering in the fluid connections, I assembled everything, just like before. And there it is, the rotary valve 2.0. Let's test it out. This works really well. And with a full rotation, the valve cleanly switches between the two inputs. With it working, let's try to turn this into a walking robot. Remember our original idea? Building a microfluidic chip with legs. Based on the earlier valve experiments, I developed this new design. Positive pressure is routed to a central port, while negative pressure connects to an outer circular groove. Between these two sit three output ports. On top, the rotor carries two sets of bridging channels. Two outputs are connected to the central port and the third to the outer ring. As the rotor turns, this connection pattern cycles, producing a rhythmic sequence of outputs. The rotor itself is driven by a servo motor, mounted to the base with screws. Now, to turn this into a full microfluidic chip, I extended the three output ports into long channels that run across the entire length of the chip. Along the way, I added a series of side branches, each ending in a cylindrical chamber. These chambers form the internal cavities of the soft silicone actuators. Three of the actuators are combined into a single membrane to move one leg. They are injection molded from silicone, and they have powered the legs on both of the earlier salamander bots. The robot will have 6 legs in total, and the goal is to use an alternating tripod gait, similar to how arms walk. At any given moment, 3 legs stay on the ground for stability, while the other 3 move forward. Let's take a look at how the rotary valve activates the muscles. These 3 legs and these 3 legs are activated in sync, but their activation patterns are offset. That offset creates the alternating rhythm, and with a bit of luck it should give us a stable gait. Printing the microfluidic chip took about 25 hours. thanks to the slow speed needed for transparency, fine 0.2mm nozzle, and a 50 micron layer height. But honestly, worth it. You can clearly see all the tiny channels inside. Like a sci-fi circuit board, but for air. As before, I added capillary tubes for the fluid connections. Then molded a fresh batch of silicone membranes. Now in this super bright orange. To attach them, I printed some covers and sandwiched the membranes between those and the chip body. Seeing the orange actuators glowing through the transparent material really adds another dimension to the whole thing. Time to bring it to life. Let's add the valve. After printing the new rotor and servo attachment, I assembled the whole mount and pressed the rotor onto the servo. Before mounting everything, I gave both contact surfaces a quick clean with tape to remove any dust or debris. And there it is, spinning. It wobbles a bit, but how cool is it to see everything in action through the transparent parts? I started with a single pump and hooked up both the positive and negative input lines. But all the membranes just ballooned up. It seems like the pressure side was overpowering the vacuum. So I added a second pump for more control, one for vacuum and one for pressure. I cranked up the vacuum all the way and then slowly increased the pressure. And at some point the membranes started to move. Watching them pulse through the transparent body is incredibly satisfying. Time to give it some legs. I attached them using zip ties. And just like that, it's standing on its own feet. Next up, I mounted the motor drivers on a small board to build a simple controller. Two drivers control airflow, one for vacuum, one for pressure. The third handles the 360 servo that spins the valve. And after a bit of fine-tuning, the legs started moving. Watching them shift in sync is honestly kind of mesmerizing. And it's got a bit of a tentacle vibe. All being driven by this little spinning valve. And then it finally took its first slow steps. But from the side it was clear there was way too much weight in the back. So I added some heavy nuts for balance. And of course some googly eyes. It looks so cute. For better grip, I slipped tiny silicone tubes over the feet. Little anti-slip socks. Already walking way better. But there was one last thing I wanted to try. Switching the pressure and vacuum inputs. And that was a trick. It started working for real. Wiggly, weird, but working. And honestly, kind of adorable. It's not the fastest walker, or the most agile one we've built. But I really love this one because of what's going on inside, literally. And yes, it can also walk backwards. This felt like a real step towards something I've been chasing for a while. A squishy, air-powered robot with integrated control, built right into the body. We are still a long way from a truly autonomous soft walker, but this brings us closer. And there are so many more ideas to explore, from squishy logic gates to self-oscillating catch-up valves. This project pushed the limits of what I thought was possible with FDM printing, and taught me a ton about microfluidics along the way. See you next time, and hit that subscribe button for more squishy bots.